Welcome back. Today we're going to be talking about linear functions. Okay, a linear function is a type of function, and we've gone over what the specifications of a function are, that forms a line when it's graphed. Okay, and we're going to make the specification that the line cannot be a vertical line. If you remember, vertical lines go straight up and down. And we'll talk about that a little bit later in the lesson, why a linear function cannot be a vertical line. So it's fairly easy to see when a graph is a linear function because it forms a line when it's graphed, right? So anything that's a line, and remember in math class we don't consider, like in art class you may be asked to draw a line and you can draw something like this. We don't consider this a straight line in math class, okay? We don't even really call it a line. When we say line, what we're typically referring to is a straight line. So that's implied in mathematics, that when we say line, that it is straight. So when you have a graph and it forms a line that's non-vertical, then it's a graph of a linear function. Okay, so it's fairly easy to tell what the graphs of linear functions are because they form lines, but it's a little bit harder to tell what equations are going to form lines when they're graphed. So here are some characteristics of those equations. All variables are raised to the power of 1. No power of variable is in the denominator of a fraction. And the terms with x and y are separated by addition or subtraction. Okay. Another way of thinking about this rule is that if an equation can be written like the one below, okay, then it is linear. So this is a little bit better of a way of thinking about it. This is called the standard form of a linear equation, and that's because it has all the characteristics that we're looking for. All of the variables, x and y, are raised to the first power, right here, okay? There are no variables, and by variables I just mean the x and y because what a and b stand in for are any real numbers. A, b, and c are actually any real number. So these are just, a and b are just coefficients to x and y. That when you actually have an equation here, a and b are numbers, and c is also a number, okay? So when I say that when we're talking about variables, what I'm really talking about are just the x's and y's. So none of the variables show up in the denominator of a fraction, and the term with x and y are separated by addition or subtraction, okay? And the only specification is that a, b, and c are any real numbers, so that's irrational or rational numbers. Okay, they could be pi, they could be the square root of 2, it doesn't matter, as long as they're not imaginary numbers. But a and b can't at the same time be 0. Okay, so a could be 0 separately, b could be 0 separately, but they cannot be 0 at the same time. This is a linear equation, all right? Let me give you some examples of equations that are not linear along with their graphs. So these are nonlinear equations with their graphs. So as you can see here, this it doesn't fall, the first characteristic fails. So you have a variable here that's not raised to the first power. When that happens, when it's the x variable that's raised to the second power, it forms this this geometric object called a parabola. Okay, here the x and y term are not separated by addition or subtraction. So your graph is really kind of a neat looking thing. It's called a hyperbola, and it's these curves that end up in opposite quadrants. Okay, so here they ended up in quadrant 1 and quadrant 3. They could have ended up in quadrant 2 and quadrant 4. You're going to study these in Algebra 2 or pre-calculus. Here, again, you have a variable that's in the denominator of a fraction. Again, it forms a hyperbola. And here you have another variable that's raised to a power that's in the denominator of a fraction. And when I graphed it, it looked like these curves, and I'm actually not even really sure what these curves are called, but it looks like a hyperbola, like the branches of a hyperbola, but they occur in adjacent quadrants as opposed to opposite quadrants. Okay, so I'm not really sure what these are called, but that's what it looks like when it's graphed. So you can tell it's not, it doesn't form a line when it's graphed. It forms these curves, okay? And a big part of what you do in Algebra 2 is you study, you study equations, you study nonlinear equations that form curves. So that's what you can look forward to in that math class. All right, so when we have linear equations, we're going to talk about graphing them, and I know we've talked about this before, but let's look at the standard form of the equation. Now, if we recall, it's ax plus by is equal to c, where a, b, and c are standing in for numbers. So in this case, I don't see a b in front of my, my y, so I'm going to put a 1 there. So here my a is equal to -12, my b is equal to 1, and my c is equal to -4. Okay, so this is a linear. I know it's going to form a line when I graph it because it fits into the standard form of the equation. X and y are separated by addition. X and y are raised to the first power, and there's no powers of a variable in the denominator of a fraction. Okay, so in order to graph it, we've seen this before. We could choose some numbers that fit in here for x and y, but you know it's actually a little bit easier to take the standard form and solve it for one of the variables. And in this case, let's solve it for y, because all we have to do to solve it for y is add 12x to both sides. So we have y is equal to -4 plus 12x. And you might have seen this before where the x is on the front part of this equation, and that's called slope-intercept form. That's a different form that we're going to study a little bit later. But for right now, let's just take it one step at a time. It's easier when it's solved for y because or when it's solved for any one of the variables, x or y, because I can put in a value for x and I can spit out a value for y very easily. Whereas up here in the standard form, I have to think about x and y pairs together that add up in this manner, that x is multiplied by -12 added to y and is equal to -4. That's a little trickier to understand. Here I can pick some values for x that I might be interested in, like, you know, -1, 0, 1, 2, and 3. I always like putting a negative number in there so I have some things to graph on the left of the y-axis here. So if I put -1 in here, I have -12 times -1 plus so I'm putting it into this equation. I was starting to put it into the standard form, but let's put it into this one. So we have y is equal to -4 plus 12 times -1. So y is equal to -4 plus -12. Y must be equal to -16. So we have a pair right there. Okay. If I put 0 into this, I'd have y is equal to -4 plus 12 times 0. So y must be equal to -4. Okay. If I put 1 in there, I would get y is equal to -4 plus 12 times 1. So y is equal to -4 plus 12. Y is equal to 8. Okay, and so I'm just going to, in the interest of time, just sort of run them through in my head here. You should be writing down the equations, however. So if I put 2 in there, it would be 24. 24 plus -12 is 20. If I put 3 in there, that's 36, plus -4 would be 32. Okay, so I'm just going to plot these points. -1 and -16 is going to be about here. 0 and -4 is going to be about here. Okay, 1 and 8 is going to be here. 2 and 20 is here. And 3 and 32 is about here. Okay, so as you can see, these are collinear, right? All these points are collinear, so we join them with a line. And like we said before when we were graphing, we always put arrowheads on the line. We graph it as long as possible. We put arrowheads and we put the equation of the line on here. Now, I went back to the original equation. You could have put this equation on the line as well, but just put some equation on the line. So you can see that's how you can graph linear functions with solutions. We're going to come up with more efficient ways to graph it, but that's just the first level. And if you ever have to graph a function, like let's say that you had to, for some reason, graph these, you know, you're given these functions and you had to graph them, and you're like, how am I going to do that? I don't even know what it's supposed to look like. Graphing functions with solutions is always a method you can fall back on, right? Make a solution table, make x's and y's, put some values in for x, determine the values for y's, or vice versa, get some points and plot them and try to figure out what the graph of the equation is going to look like. Okay, let's look at this equation here because it's a little weird. This is y is equal to x, and y is equal to 8. Can we put it in the form of the standard form right here? Ax plus by is equal to c. So can we put it in this form without actually changing its value? Well, okay, first of all, let's put the 1 here for the b. So right now I do have the by, and I actually have the c. That's the constant on the other side. This is my c. Okay, and this is my by. Okay, now the question is, can I have an ax? Well, the trick is, okay, well, what if you put 0 as a coefficient to x? Okay, So let's check this out. We have 0 times x plus 1 times y equals 8. Does that fit the standard form? And it actually does, because we said that a could be 0 or b could be 0, but they can't be 0 at the same time. So a here is 0, but b is 1, so it's perfectly fine to put it in this form. So let me just write it a little bit neater up here. 0 times x plus 1 times y equals 8. Okay, so this is a linear equation, right? Because it fits into the standard form. Now, did I change the value from the original equation, y equals 8? I did not change the value because I added 1 as a coefficient to y, so that's okay. And I added a term that was 0 times x, but 0 times x is 0. So really, this whole thing, if you simplify it, would collapse down to y. The reason why I made it a little bit more complicated is because I wanted it to fit into the standard form of the equation. Also, it makes it a little easier to fill in a solution table. So let's choose some values for x. And I said, I usually choose a negative value, and let's choose -1 and 0, 1, 2, and 3. I like to choose 0 for x a lot, so that it's a little easier to figure out a value for y. Okay, -1 times x is just 0, right? So it would be 0 times -1 plus 1 times y equals 8. Well, this is 0 plus 1 times y is y equals 8. Y equals 8. Okay, so y is equal to 8. Let's plot that, -1 and 8 right here. Okay, let's try a different one. So we have 0 times x. So we have 0 times 0, right? We're plugging it into this equation right here. Plus 1 times y equals 8. Well, 0 times 0 is 0, plus 1 times y is y is equal to 8. This is just y is equal to 8, so y is equal to 8 again. So you have 0, 8. Okay, so you might be seeing the pattern here. If I put 1 in here, I'd have 0 times 1 plus 1 times y equals 8. So again, we're going to get 0 plus y equals 8, or y is equal to 8. And so as it turns out, all of these values are 8. It doesn't matter what the values of x are, because you're multiplying those values by 0. So all of these things, you end up getting this line that always has a y value of 8, regardless of what the x value is. What does that look like? It looks like a line. It is a horizontal line that has a height of 8. So let's write these things down. So it's a horizontal line right here that has a height of 8. Okay, 8 units, positive 8 units above the x-axis. So let's go back to the original equation right here. Y is equal to 8. Well, think about how that makes sense in terms of the equation. Y is this is our height measurement, right? It's basically up or down, right? On the xy coordinates. So, or on the two-dimensional plane, it's our height coordinate. Well, what this is saying is it's saying it's a line whose height is always 8. Well, what does that look like? Because usually if a line is diagonal, the height is going to be different at every single point, right? But this is a line that's very different from the lines that we've been seeing. It just means that it's a line that always has a height of 8. That means it's a horizontal line. Okay? So anything that has a form y is equal to a value is going to be a horizontal line. Okay? Okay, let's go over an equation that has that looks very similar to the one that we just did, except it has x is equal to -1. So again, I could force this to be in the standard form by putting 1 as a coefficient to x. So I have 1x plus 0y is equal to -1. Okay. Now in this case, we have to choose some values for y, because I'm going to be determining the values for x here. So here, let's choose -1 here for y, 0, 1, 2, and 3. So we'd have 1 times x plus 0 times -1 is equal to -1. 1 times x is just x. This ends up getting 0 is equal to -1. So x is equal to -1. Okay, just like we said, x is equal to -1. So it turns out that anytime I put, we could replace this with 0, right? 0 times 0 gets 0. And so x plus 0 is -1. X is equal to -1. We could have replaced this number with, we could replace it with the next one, which is 1. right? So 0 times 1 is 0, x plus 0 is -1, x is -1. So what this is saying is it doesn't matter what the y value is, x is always -1. Now let's go ahead and plot this. -1, -1 would be here. Okay, we would have -1, 0 here. Then we'd have -1, 1, and so on. So what we have is we have this vertical line. Okay, so here we have this vertical line at the value of, that has the x-coordinate of -1. So every point along this line has an x-coordinate of -1, and it has a horizontal distance of left by 1 unit. Okay, so all of the x-coordinates here have the same value, which is -1. So it turns out that x is equal to a value here, some constant here, means it is a vertical line. Okay. Now we said we would talk about vertical lines in just a second. At the beginning of the lesson, we said that we would talk about them. Well, this ends up being the difference between a linear equation and a linear function. Now let's look at this equation. We said that we could turn it into the form a times x plus b times y equals 1. Okay, so we said that this was 1 times x plus 0 times y equals 1. A and b aren't the same value. A, b, and c are all real numbers. So we know it's a linear equation, but this is the one exception to a linear equation resulting in a linear function. This is not a linear function. If you look at the coordinates that satisfy it, right? So these were the coordinates last time. We could come up with coordinates here. So we would have these coordinates right here. This is let's see, 1 and 0. This is, let me write it here, 1, 0. We would have 1, 1. We would have 2, 1, 2, 1, 3, and so on. 1, -1. We could have 1, 1/2. We could have 1, -pi if we wanted to. What this is saying is, remember, this is this function. 1 is being sent to 1, 2, 3, 4, right? This is our example where, using the mapping diagram, we can indicate that this is not a linear function because one value is being sent to an infinite amount of places, okay? So this is a vertical line is not a linear function, but the equation can be turned into a linear equation. So this is where you have to be this is the one exception to the rule that a linear equation turns into a linear function. Okay, so that's the end of the lesson for today. We just learned how to graph linear functions with solution tables, and we learned about linear functions that result in vertical and horizontal lines.